that Alice cannot send any information to Bob when she wants to use the different measurement inputs. So actually, based on these notions, this implies that when we sum over A on these gamma matrices, it has to be equal to the intramoment matrix has to be equal to a summation of A of this gamma AX prime for different measurement inputs X and X prime. And after applying these no signal in time constraints, we check this temporal Bell inequality again. So we obtain about 2 square root of 2 for this case. Okay, so here we can see that the third one and the fourth one give us the different or the more strict upper bounds. And this actually provides us a very important applications. So exceeding 2 square root of 2 certifies that either the underlying QB measurements are full rank or there exist one-way communications from Alice to Bob. All right, so let me summarize the talk today. So first we introduce the framework called the intramoment matrices. And this method can be used for characterizing general quantum temporal correlations. And then we can use these intramoment matrices to maximize the temporal CHU inequalities with different constraints. And for more details or more applications, if you have any interest, please take a look at this paper. Okay, so finally, I would like to thank Jens Eisers from Free University of Berlin for his collaborating this project with me. And also, I would like to thank National Science and Technology Council and the National Center for Theoretical Science for their financial support. So with that, I would like to thank you for your attention.
Any questions from the audience? Yes, please.
Hi, thank you for the wonderful talk. Your methodology seems very similar to the NPA hierarchy, right?
Yes.
So I was just wondering, is there any conditions like rank loop constraints, like similar to the NPA hierarchy, which tell you like you have achieved the optimal value or something?
You mean in the NPA hierarchy, do they use the similar constraints?
No. So they have the rank loop condition, right? So that they know, okay, they have achieved the maximum value and they can tell, okay, that the correlations can be written in the Bond rule, using the Bond rule.
You mean for the rank constraints?
Yeah.
Yes. So there actually is a paper by Navasquez and Vertices. They also propose use the rank constraints to bound different for bounding different types of Bell inequalities. So here, actually, the spirit is very the same, but the difference is that we consider the temporal scenarios. So and from here we can also and because the rank constraints that we are going to impose is on Bob's measurements. So here we can actually very precisely to see or to impose these constraints on Bob's measurements. But as I know that in a Bell type experiment, if you impose these rank constraints, I'm not pretty sure, but maybe you cannot distinguish you are imposing the constraints on Alice's parts or Bob's parts.
Questions?
Thank you for the talk. So this methodology, if we consider other type of inequality in the temporal correlation, like if you compute like 3 times LGI, like M1, M2, M3, and the correlator inequality considering that, then we can compute also the quantum bound corresponding to those.
Can you say again, please? Can you say again? Sorry.
Okay. So the inequality here you have considered, it includes like 2 times correlator.
Yes.
If we consider like 3 times correlator, so this can also means the quantum bound can also be obtained.
Yes, I think so. But actually, in our paper, we also consider that in a temporal scenario with multiple points of times, so you don't have to restrict only 2 points of time. And for multiple points of time, you can develop also the very similar intramoment matrices but the structure will be more complicated because you are consider multiple point of times. So the Hilbert space of this or the dimension of the instrument matrix will be larger. So maybe I think the disadvantage is that when you try to compute using the computers, actually it requires a lot of memory resource.
Okay, thank you.
Okay, Yongchen.
Shin, I just want to clarify a point here. So if I understand correctly, all these gamma AX, they
yes.
are just moment matrices for the conditional states, post-measurement states. Right?
Yes.
So there should be some constraints relating all these different gamma AX, let's say for given X, for the same X, right? Because they are coming from the same inputs but for different outputs. But do you have that constraint here? Because you say that you are only having these positivity constraints, or you have something else in addition to that?
So if you are talking about the positivity of the moment matrix, okay. So if you are talking about only first part, yes, the positivity constraint is only the only constraint. Because
maybe we discuss offline.
Okay, yeah.
I have a question. So
there's another one.
anyone? Yes,
Hi,
please.
thanks for your nice talk. Using this approach, you demonstrated certification of non-projective measurement, right? So have you also looked at certification of dimension? For example, you take some contextuality inequality. Can this technique be applied to other inequalities such as contextuality inequalities? Using contextuality inequalities in the temporal scenario, certification of dimension has been demonstrated. Can your technique be applied in that context too, to certify dimension?
So if I understand correctly, you're asking about if we can use other types of inequalities to certify
contextuality inequalities.
Yeah. So in general, I think so, but in practice, I'm not sure if this is the case, because we don't. So this tool is not designed for testing the temporal CHS equality, but it's a general way.
Okay.
Any questions?
I would like to ask, like, you said that if you get a value like larger than 2 square root 2, then you can make sure like it is coming from some maybe 4 rank measurements. But could it come from maybe dimension larger than 2, but projective measurements?
So can you say again? Sorry, I didn't hear very clearly.
So you say if you get larger than 2 square root of 2, and if you have a condition like dimension equals to 2, then you can make sure that your rank will be 4 rank. But if now, if you have something like dimension larger than 2, can you still say something about your
Okay,
rank?
I see. Yeah. Okay, so actually we don't care about actually when the dimension is set to d is larger than 2, because when you as I remember, when you set that d is equal to 3, then it shifts the bound of 4. But when we talk about when we talk about the value of 4 as the upper bound of this inequality, actually it is trivial because it is an algebraic maximal value of this inequality. So that's why we don't want to talk too much about when we obtain the bound of the value of 4, because from our algebraic point of view, this is a trivial bound.
Yes, do you mean, like, for example, if dimension equals to 3, you can get something closer to this algebraic form?
So, okay. So if I understand correctly, you mean if we test the dimension equal to 3, can we see some different bounds or?
Yes, because in the end you are looking only at the correlation. So how could you make sure like what dimension you are using now?
Okay, yeah, so for my computation